Okay, so highest degree is in this is 4. Now what is interesting, or in the usual notation, see, remember, so whenever though it is a degree of polynomial is 4 here, the missing term, the exponential x3 is, the term is missing. Okay, but that doesn't mean that it is, it means that coefficient of that is 0. That is how we represent that. Okay, so though some of, so this will be, information will be helpful when we go for addition of that. Okay, so when I want to do a addition operation, we'll consider, we'll see how it has to be done. Okay, so this is related to the your polynomial. Let us take two polynomials and try to do some operation on that. This is well known, you already know this concept, but just to see how I can implement using a linked list, that is what we require to learn here. Okay, so the example is taken as a two concept. One is a sum of that, another is a product of this. Okay, in case of sum, the whatever the user have entered, the degree will not change. Degree in the sense the length of that is going to be varied, no doubt, but in case of product we are multiplying that, so degree is going to change for us. Okay, now let us see the two polynomial. It's a randomly taken. So we will give a provision to the user to enter this kind of any kind of polynomial. So they can enter, now what all they can enter? They can enter the coefficient of that and the degree of that. Am I right? So if I want to represent this as one node, see, understand, I want to represent the polynomial as a linked list. So I'll be referring this as one node, and this is another node, and this is another node, like that. Okay, so how many entry, the whatever we have the polynomial, this one, we will be using that many nodes in that. So whenever I have a node, so what all it should consider, the structure of the node. Now decide, there should be something to take a coefficient of that, something to take your polynomial, the degree of that. Okay, what is the value of this exponential? Okay, so that is how I have to take. Now whenever I have minus sign, the coefficient is considered as minus. Okay, so that is how you have to consider. So there will be a structure we have to build for that. Okay, now to see the how I'll execute the sum of this. Okay, so it is already known to you. I can't add these two terms because we will match with the degree of these two values. Okay, so the first value of your a is the ratio, the degree is 3 here and degree is 8. I can't directly just add as it is. The coefficient cannot be added. You already know that. Why? Because we consider the we have to match the degree of this. How we do that? The coefficient related to the x raised to 8 is considered to be 0, and we'll just add to this. So it will become a x raised to 8 or something. It is known to you. Okay. So what we do, if you think if you want to implement in a program, how I should be using, you think in that direction. Okay. So we'll search the two polynomials. To given the information, we'll just check the degree whether it is matching. If it is matching, whichever is highest, we will keep as it is. There is no change in a coefficient value. Okay, now then we move the whichever is, we consider the degree of that, the next node, we are forwarding to the next node of this. Then we'll match these two and we'll check whether it is, there is a match in the polynomial, the degree of this, whatever the value, the exponential value. Again, it is a 3 here, it is a 5 here. Okay, so they don't match. So we'll retain as it is. Okay, so that is what you have done here. Now we just forward the pointer of this, the linked list part of that. Okay, then we'll try to match these two. Okay, so in this case, the degree, it is also x raised to 3, this is also x raised to 3. So the coefficient of this is being done the arithmetic operation, the addition. Okay, the whatever the result, we'll store it in the that node, whatever we have. Then Now, when both are matched, you are required to proceed for both of them. The pointer of this has to be proceeded same direction. Okay. Yes. Any doubt? Okay. Now you have moved the pointer here. Say for example, now you try to see there is any element with the x raised to 1. Okay, x raised to 1 is nothing but that only. So in this case, we don't have that term. Okay, we assume that coefficient to be 0. So we retain as it is. Then we will increment this particular form and until the your polynomial get over. This is how we will be doing in a programmatic form. Okay. Now what is you have to observe? The given when the user enters, it is dynamic in nature. We don't know how many nodes will be there, and when we do perform any arithmetic operation, still we don't know how many nodes will be there. Okay, so that depends on the addition. Similarly for the your multiplication, so we are multiplying two polynomial. Yes, any doubt?
Start recording.
But oh, so sorry. Thank you. I will do that. Thank you for reminding me. Okay, so I'll just start again now, just with this polynomial. So we have taken two polynomials. Okay, and what is the nature of this polynomial is the user can enter randomly its values. Okay, so there will be a degree, whatever the polynomial value, and a coefficient value. So the user can give any kind of polynomial. So it is dynamic in nature. Similarly for the b of x. So when we perform any arithmetic operation, again the result is also going to vary in length. So this kind of application, the linked list is supposed it is the best option for us because we don't know, it is decided in the runtime only. So the best suitable chance will be the your linked list rather than the array. Array we have to decide. Okay, in earlier with the, or you can decide say very high value of your memory allocation for that. But still I have to take two information. See the in array, if you remember, it has to take only the same kind of element. So implementing a similar kind of the, because array should contain only one type of element kind. Okay, so implementing with the array is going to be difficult, whereas linked list will be suitable, more suitable for this. Okay, so when we have the answer to be a, or the result is very dynamic in nature, the linked list is going to be more appropriate for this. Okay, so this is example for addition, this is for the multiplication. Now let us try to implement this using a program. Okay, now if I want to do a program, this will be the algorithm to add two polynomial. How we do that? Let p and q be the two polynomial, as in a previous case a of x and a b of x, say for example. So while p and q are not null, what do you mean by not null here? Whenever we declare, we are trying to implement by the linked list, say for example, we require to say whether they inserted the some value in the polynomial. If the polynomial is not at all initial, just it is declared, then there is no value contained in that. So we are checking initially is there is any value to assign for p and q. That's the reason we are taking it as a not null condition. Okay, so if you find there is a value for p and a q, two polynomials, okay, then you require to check for if the power, because we, if you want to do the addition, you require to check the power whether they are matching. What do you mean by power? The degree, the whatever the value, x raised to values. Okay, so whether they are matching. Okay, the power of two terms are equal. There can be three conditions. It can be equal, or p can the polynomial, the value of the power of the p, the initial, the term of that may be greater or a lesser. Three conditions. Okay, so you require to write a appropriate code for that. Now let us take the first condition, when they are both the polynomial values are equal. Then what is that done? If you don't, this is what your, if the coefficient happens to be the same, say for example, in this case, okay, see here 3 minus 3, the coefficient happens to be the same, so they will cancel out, the coefficient happens to be 0, so this will be missing here, okay. So the term in the x raised to 3 will be missing in the answer here, okay. So just to avoid that, creating a node, because otherwise we have to create the node for that. So first of all, you're just checking the whether coefficients are going to be cancelled out or whether there is a value for that. If there is a value, then only create a node for that. Okay, that is what you have done. Then when you have done the addition, you have identified there is no cancelling of the values. Then insert the some node for that and advance both the pointers. We'll see that. We'll see with the example. Okay. Now what may be the another condition? When p of that, this is this condition. When p of this, okay, whatever the another one is, this is a p. Say for example, this is p polynomial. This is q. First of all, you are just checking the what is the degree of that. Okay, both of the values x raised to power, whether they are matching. If they are matching, you are making both the pointer advance. If not, you are just checking which of them is greater. So if in this case, say it is a b of x is greater, then you are incrementing the linked list, whatever the reference value to the next, only for the b. Otherwise, you are incrementing this. Okay, that is what you have done in a next term. Depending on whichever the power is greater, you are retaining that term and advancing its pointer. Okay, so this has to be repeated when till you complete your whole polynomial list. Okay, that is what you have done here. Okay, this is the algorithm to implement. Now let us take an example or we write a program and how it can be implemented in this. Is it clear? Any doubt in this? If you understand this algorithm, we can implement either in any of the language. Okay, so is it clear? This algorithm is clear to you? Yes, respond. Is it fine? You want me to explain again or is it fine for you? Please respond. Is it okay? Did you follow?
Yes, ma'am.
Okay. So this will be the program for that. So what you have done, observe here. So you have declared a structure here. Okay. The structure is some node. We calling a polynode or something. So it is having a you can placeholder for taking the coefficient and exponential value. And there is a head. Head is nothing but always remember in the linked list implementation, this will be initialized to the null. Okay, initial. Whenever we create, there will be assigned to the null value. Okay, starting point for that. Okay, so there is a one more. This is implemented by the singly linked list. So there is a one reference value which will store the next address. Okay, so basically you are creating a structure to hold a coefficient value, exponential value, and a next address of that. Okay, this is a structure. Then these are the methods which will be called. This is a destructor for us. Okay, why we call the destructor? Because otherwise, if you do, because we are creating them in a dynamic way, if you don't release them, it will be there in that. Okay, so junk value will be there, and memory utilization will not be proper. Okay. Now what is done in a constructor? If you recall, this is a scope resolution. Either I can declare here only or I can put it after the class also. So this is a scope resolution. So this is a constructor for us. Okay. So this is, there is no parameter. So it's a default constructor. But what you're trying to do it here, it's a user defined. Okay. So head is initialized to null. This is a must. Okay. Because in all our next program, we'll check whether head is null. If you don't initialize in a next value, if you don't initialize, it can be any random values. Okay, so we should initialize to null because in a next iteration we'll be checking whether there is a null or not. Okay, so as soon as you create any object of a poly, Okay, what happens? It is initialized with a head, and one structure node will be created for that. Okay, this is how the structure. So there is a placeholder for quotient, exponential, and one reference value, the address for that. Okay. Okay. Now let us see the read of that. Read is nothing but again the user can enter any number, any kind of, it can be, if I take a same example, a of x, okay, it can be any exponential value, any quotient value. So there is a provision, they can give a randomness in this. So what you're trying to do here, it's a y. If you want to enter, you want to proceed here, that's why we are just checking whether it's a capital Y or a small y. So initially you're declaring it as y because you want to take that value. Okay, so you temporarily some head is assigned. This is what you're doing. It is a copy constructor kind of. Okay, you're just assigning some temporary value. Okay, so what you're trying to do, if temp is equal to null, that means you're creating a new node. So whenever there is no node created, there is no, not at all, initially you're constructing, this is construction, so it will call the your constructor, default constructor, and say it is initialized to null. That's why you're checking here null. Okay, so you're creating now new node with the whatever temp, you are assigning the same value here. Okay, then you are assigning this all the reference value. We'll do this afterwards. Okay, so you are entering the quotient of that. Okay, there is a placeholder. Okay, now how you do that? This is a temporary, this is a node, and its quotient is taken, whatever you enter is being put into this placeholder. Then exponential value is hold in this. Initially, whenever you enter the values, you are not, we don't know what is the next connection for that. Okay, so we are entering the reference value as a null for this. Okay, and you, whenever you say it is y, the next value, it will come to this again. Okay, so that is what it will proceed. Now how, when this will enter to the your else case, whenever the initial only on for the first value, it will enter to this particular value. Head is null at that time. Otherwise, it will enter here and a link is created for that. The reference of that is being stored here. The link is nothing but a reference value. So it will be storing the address of whatever you created. So this is how you are trying to take your node, say for example polynomial. Now to take an example, just let me take one example. So initially, remember, head is stored as a null. Okay, whenever we create any object, this is what you've done. Okay, you're initialized to null here. So it will enter here and it will just create one node. Okay, what all structure it contains? The structure is basically if it is a single node, whatever we have, this itself, data itself is stored, divided into one to hold your quotient. I will put this. Okay, one to hold your exponential part. Okay, then there is a reference point here. Okay, this quotient is taken here and it is stored here. Say for example, I'll take 3x raised to 3, say for example. So this part is stored here. X is not at all stored here. Okay, this is, we are just representing. Afterwards, if I want to print, I will be just giving a value. This is not at all taken, though we are referring like that. So it is, storage is there for taking the quotient, and there is a storage for the exponential part. This is just a representation part. This is not at all taken. While displaying, we'll just I can display this as 3y3 also, or I can display this as 3z3 also. There is this Z or whatever alphabet I'll give you, it is a when we go for display. But what is important is the quotient value and exponential value. So we are having only the placeholder for that. Okay, so don't be under impression how we have stored this value. So we are not storing this. Okay, it's just a representation for us. Okay, so whenever we create one more, say for example, the user says one more node has to be, they want to enter one more value here. This is until y to add more nodes. Say for example, I say yes. Then what is done? You create one more node here. Okay. Again with the same information, but at that time initially it was head was null, but it is afterwards it is updated to the first value. Okay, first value. Say for example, it is 2000. Okay, now head is referring to this. So this will not go to the temp here, it will come here. Okay, so what has happened here? See, temp link. Where is the temp? Temp is still referring to the your node here. Okay, where it is referencing to this temp. Its link is now pointing to the new node. Say it is created at 5000. This address is being stored here. That is what is done here. Okay, and you are updating with the temp link here. That's all. So whenever you create a new node, its address is being updated in a previous value. Okay, previous reference. So now you have created one more polynomial placeholder for us. Okay, sorry, not polynomial, the next order. Say for example, I want to take 2x here. So this will be the coefficient value. Minus 2 will be the coefficient value. And what is the exponential value of that? It is 1. So it will be storing minus 2 and a 1. And if I have say plus 4, say for example, then I'll be creating one more node structure basically. Okay, and what is done here? You will be storing what is the coefficient here? It is a plus 4. Okay, and what is the exponential value? X raised to 0. If you remember, any this one raised to 0 will be 1 here. Okay, so that is what is stored here. It is not division, don't be under that. So you have two parts in your memory. Okay, so this will be the now stored with the null here. Why? Which condition? See this. Initially, whenever we create any node, you are storing its link with the null until you say yes to that. Okay. So when you say yes, it will be updated with the temporary address. Otherwise, it is stored by default. It will be stored with the null here. So what happens? This is how you are creating the linked list to hold all your polynomial. This is how you do the polynomial. Two polynomial. I can create two objects by this method. So I can take any polynomial with this. Is it clear for you? Is it fine? Please confirm. Do you want me to repeat? Is it okay? Students?
Yes, ma'am, it's okay. You can continue.
Okay. So this is how you're done. Next is what the displaying. I don't discuss much on that. What you're trying to do, whatever the nodes are there, you're trying to see where can I display that. So you're just checking the null, and if coefficient is there, you're displaying appropriately for that. Okay. So this is the same as displaying any of your singly linked list kind of. Okay. So I don't discuss much on displaying your polynomial, but pay attention whenever it is exponential. Here use the method. So you are having a placeholder. Say for example, I have a placeholder. This is 3 and 3 and the address for the next. Okay, so I have 2x. I have taken minus 2 and power is 1 and address for the next. And I have what I have taken, I 4 I think so. So I have taken 4 and its polynomial is 0 and this is null. This is how I store it. Okay, the address of this is here. Okay, so each one is referring to the address of this. But when I print this, see this, there is a one variable. You can take either x, y or whatever value. So while printing, I'll take 3. This is a coefficient value. Then I'll say the power, and this is how I'll write. This is minus here, the coefficient value. So this will be printed in this form. Though I can write 1 or I can leave it, no issues. But this is how it will be printed for you. Okay. So 4 raised to x raised to 0 like this. Okay. So or you can just again check that whether if it is 1 or 0, you can just omit that, or how you want to. This x raised to 0 can be just the 1 here. So that is how it will be print. Okay, so while printing only we are just taking, but while storing the node we are not doing this anything. You can just use this with the Y or a Z, any kind of alphabet. I hope it is clear for you. Okay, so that is about the displaying of that. Now I want, this is very important. Now for example, I want to add the two polynomial. Okay, so as I discussed, okay, there will be three conditions for us. We created, observe here what we have done. Observe, we are sending the, what is this, address of that polynomial. See, this is not just the object, it's address, because it's a pointer for us. Okay, so we are sending the address. Two polynomial objects are created and its address is being passed to this. Okay, so this address, so it is pointing to the head of that. So we'll be having a whole object along with its reference value. So there are two, it is that linked linked list. Basically we refer them as a polynomial. Okay, so L1 and L2, I'm checking whether they both are not null. Basically if it is a null, then we don't do anything in that, there is no operation possible. So if it is not null only, we are going to do for the other operations. So we'll just check and we'll return to that. Okay, so this is a temporary tool for doing your calculation. You can call, you can think of the moment I create this, it is a pointer to that. Okay, now what it done, we are assigning these two, again the copy constructor. If you are joined with the C++ class, this is where we are using a copy constructors. Okay, we are creating the objects of this is being assigned to this. Okay, so already it is created here. Okay, it's a reference value. So what is done here, you are assigning this temp1 with the header value. So initially, if you remember, it is the null value for that. Okay, head is assigned with the null. Okay, if it is created newly, but in this case it is not created newly, it is being passed to this, so there will be some values to that. Okay, so that is what you are checking. If it is nothing is there, you need not do anything. Otherwise you are just checking, but still you require to check here, or you can anyhow you have done here also, no issues. Okay, so you are making use of, if there is no null or kind of, then you are trying to go ahead. Here you are just created one temporary value here. Okay, that is not much, just for the all the error handling. Now let us take the exact one. So initially you want to go with the operation of that. These are the two conditions. What is that first condition? I'll just go here. This is new node Z, that is a new whatever the operation. Whenever you perform any addition, you are storing that, that is a result part, that is Z here. Okay, so in this Z, okay, you have created a node for that. Now you are just checking the two values, the exponential values. So I'll take two examples, simple example. Okay, now what I'll take one, say, what is the name? I'll just take the same reference so that it will be used. Say, I'll take what is the temporary, they have taken temp1 and temp2. So I'll just take temp1, say for example, a simple one. I don't go much. X raised to 3 minus 2x plus 4, and I have temp2, okay, which is simple x plus 1, simple one. Okay, so what you're trying to do, I want to add these two. So what will be the answer? You already know the answer. So the answer is, first I'm checking the polynomial of this, the exponential value. If they are matching, then only I'm adding the things. But in this case, now what is done? You're checking the exponential of this and exponential of that, and you find exponential temp1 exponential is, see this is temp1 and its exponential is more than the temp2. So this condition is executed for you. So what happens, that coefficient, it's a newly created node for us. Okay, so its coefficient is just retained, temp1's information is retained. So if you see the Z here, so the initially one node is created, whichever you created, its coefficient is going to be the temp1 coefficient, that is 3 here, and its exponential is going to be again I'll just write x raised to 3 just for your convenience, but otherwise we'll storing 3 and a 3 here, and its link is now forwarded. Temp1 is equal to temp1 link. That means the next it is being taken the its address. This is a linked list for us. So this address is now taken the wherever we created. So that again this information is compared with this particular information. Okay. Now what happens in the next iteration? This 2x and this the whatever exponential value is matched here. Okay, so if it is matched, what happens? This is equal condition. Okay, so both are matched here, so the coefficient is going to be the sum of those two, then its exponential is retained and both temp1 and temp2 link is taken. That is what you're proceeding. That's how you're doing the information. So if I come back to this, in the next case, you're adding both of them. -2 plus 1 is nothing but -1. Okay, and it is x here. Then both the pointers are proceeded like this. Okay, so they are taken the next one. Then both of them are checked for the exponential value. Again, it matches here. And what happens? You are doing arithmetic operation. 4 plus 1 is going to be 5, and exponential retains to be 0 in this case. No change in that. And you come to the end of that. That's all. So you come out of your loop. In the another case, say for example, this exponential is more than this particular one, then your pointer for this will be moved. Okay, that is how you do the changes. You are checking for the exponential part. If they are matching, you are doing the arithmetic operation. If not, whichever is greater, whichever is having a values, greater values, its linked list, whatever address is being proceeded, so that you are just referring to the, you can do a arithmetic operation properly. Is it clear for you? This is for addition. Is it fine? Is it clear? Yes, students. Can you respond?
Yes, ma'am.
Okay. So this is to add two polynomials. Now, this is when you do the new polynomial is done. That is the while you are creating whole coefficient in the for all the you're running for this. Okay, that's all you're doing here. So now let us do the what is they how they created the destructor part is being put here. Okay, this is how you call that, and how you have to proceed for when one of the linked list is null, what to do that. Okay, so you are retaining only one of the polynomial here. That's all you are going to do it here. A simple concept here. Okay, so that is for the addition of that. Okay, so this is how the user can enter the polynomials, first polynomial, second polynomial. You're calling the read operation of that, and you're taking the new one. This is the another method where you're passing that to polynomial whichever you created to that particular program function basically. So this is how you can display. Display is nothing but you're using those, you're displaying both of the polynomial and its answer for that. So I don't go in detail of that you can do that. Okay. Now this is very interesting here. Multiplying two polynomial. What do you mean by multiplying here? Remember in the previous one, we are just comparing the the exponential part. Here we need not do that. Okay, we have to multiply both of the polynomial whatever be, so the length is going to be different, even the exponential part is going to be different. If you see now again the placeholder, we have one placeholder for the coefficient, one placeholder for the exponential, and one for the your reference value. Okay, so again this all remains the same for reading and polynomial, only multiply it will be bit different. Okay, again remember we are sending the address for that. Okay, and this is important one, whenever we create we have to put a null in that. Okay, this is your constructor for that. Destructor is nothing but, since we created the your new kind of, so we have to remove all of the things. So we have to detach, we have to remove this head. The moment you delete this head itself is a pointer for us, so you require to delete all the things. Okay, so that is what you have to do for a destructor part. Okay, now this is the read. I don't go into the reading, it's the same as the previous one. Even a display is the same. You would have we can introduce the same what is the function. Okay, so this is where I'll be highlighting here. Okay, so I have to multiply two polynomial here. Okay, so again you have taken two temporary values and you are assigning here, and you're checking they are not null. That means if they have some values in their linked list. Okay, so what you're trying to do, you require to multiply. Remember, in the case of multiply, now what is to be done, I'll just tell you. This is what is the main part of that. Okay, both of them, while there is not null, you are just executing this particular information. Very simple. The multiplication happens to be very simple. I'll take a same example. Say p is equal to, or temp1, I'll just go with that. So temp1 is something 3x cube minus 2x plus 4, and I'll take another exponential as it is. I don't remember the coefficient, but I'll just take that. Okay, okay. So these two are what I want to multiply. I need not check whether they are equal or not. How you do that? You're just multiplying this with its exponential part. Okay, the whatever. Whenever you're doing a multiplication of exponential, it's just the addition there. Coefficients are multiplied. That is what you're executing. Its coefficient is multiplied by its coefficient and you're getting the values, and whenever the exponential part, you're just adding them of that. Okay, so x3, and whenever you multiply with that, it is going to be 4 for that. That is how you're going to do that. Okay, and you increment both of them, you are incrementing, but this has to repeat. So this is the inner loop. X is multiplied with the whole temp1, and it is multiplied with the again temp1. This particular only the change in that. Okay, so this is temp1, again it is a temp1. So you require to repeat this loop until this particular information. That is why you have put a while here. Okay, so first time it is multiplying with the x, next time you are making a header is being linked. So this particular information is taken and multiplied with the same content temp1. Okay, that is what you have to execute here. Okay, I hope it is clear. And the length of that is nothing but the newly created is going to be retaining your new information. So that is what you are already there in that. Is it clear? Hope it is very simple. Compared to the addition, you require to check while doing any addition or subtraction, you require to check its exponential values, whether they are equal or not. Okay, that is not true, need not be done for your multiplication, but it has to be repeated for the whole information has to be multiplied by the one node. If I say the linked list of that, this is one node and this is one node. So one node is multiplied with the whole temporary one linked list. Again, another node is being multiplied with another the linked list of this. That is what you require to do it here. Hope it is clear. Is it easy? Multiplication is comparatively easier compared to your addition. Okay. So this is how same thing, the what to be done in you have put it here. So ultimately that is the multiplication part what we have discussed. I don't go in detail of that, just to complete your program it is being written here. Okay, so any doubt in the multiplication? Is it clear? The concept is clear to you? You require to run a while loop until this ends, and you require to multiply for whole the linked list. It has to go to the whole complete one iteration of until it completes the null. It finds a null here. Is it fine? Okay.
Yes, ma'am.
Okay. So let us go for the multiplication. It is just the display. I don't do this. Just representing the information. Okay. That is how. you can see the power of your linked list. Whenever I have dynamically represented information, the linked list happens to be the handy, or it is more effective than creating in the advanced kind of in the case of array. Okay, so I can use a linked list better, but again handling charge is there, like you have to maintain the linked list, the header values as well as the reference values or address for that. So there is a you have to pay the that much of memory for that. Okay, okay, so that is about one example. You can find many examples with the your linked list. Now let us go the very small part of your this is already there in a C also. This is called as a recursion. So how it is already discussed here. So recursion is nothing but reoccurring. Okay, I'm calling the same information. I'm doing doing the same thing again and again. Okay, so that is sometime it is in most of you say I want to calculate the functions where I'm repetitively calling its information. Same thing I'm doing. So it is called it will be useful for a recursive. We call this as a recursive function, or you can name that a function is calling itself. Okay, so many time I can call until there is some condition to exit. Okay, so I'm repetitively calling itself. Okay, that is the recursion program. It is well known in, I think, whenever you calculate say 1 into 2 into 2, if I want to get any polynomial or recursive, that is how you do it for a progressive approach. We'll see that. We'll take one example on that, and we'll come to that. But be careful whenever you declare a recursion, you should make sure it is not in a infinite loop, otherwise it will not come out of the loop. Okay, that is a very important point. So when you require to mention a condition when to come out of that loop, otherwise it will execute and it will be the never ending loop kind of. Okay, so be careful in defining that condition. So that base criteria, if you see, there must be at least one base criteria or condition such that when this condition is met, the function should stop, otherwise it will be a never ending loop kind of. That is the main criteria or important information what you have to do it. Okay, now what is a progressive approach here? The recursive call should progress in such a way that each time a recursive call is made, it comes closer to the base criteria. That means you are reaching to this condition to exit, come out of that. Okay, so there should be a convergent. You can think it should be convergent. It should not be going away from that. Okay. So it should reach to the condition. Okay, then only it is possible to come out of the recursion problem or recursion condition. Otherwise it will be going out of the your criteria. Okay, this is I will go with the examples only. So already know the you might can you give me one example where the recursion is being used or more popular? Can you give one example which is known to you? It is not a new thing. Can you give me a where I can use appropriately this recursion? Anyone? Yes? Where? What is a suitable one import or one very popular example of a recursion? Yes, anybody can help me here? Students, are you aware of a recursion or not? Is it a new to you?
No, ma'am, it isn't.
Yeah, but can you give me one example where a recursion can be used? Yes.
Fibonacci factorial.
Yeah, factorial. That is most of the time wherever we give a recursion as a discussion, the factorial happens to be the first one to discuss because it's a repetitive call of that. Okay, so the factorial or Fibonacci both are the same kind of. So we are doing the conditions, or we are checking conditions, and we are trying to iterate the same, or we are doing the same thing. We are calling the same function again and again until the condition is met. Okay. So those two are the important example. You can say it's a well-known example for that. But what is important to know here is we store this as a stack frame. If you remember, first this one I explained about a stack. Stack is nothing but last in, first out. Okay. It is a last in, whichever is at the top is taken out first. Okay. So last in, first out frame. Now let us see what you mean by last in, first out, or it's a stack frame. Okay. So what is done, if you remember recursion, say for example, if I want to calculate the recursion, factorial of n or something, you are calculating till you are decreasing this value, n minus 1, n minus 2, so on so forth. Then your whatever you calculated at the first will be kept here, f of n. Then you're just, so whichever is calculated at the last will be kept in the first of this. So it will be similar to the your stack operation. Okay. Last in, first out. Okay. So that we call that a stack frame. Okay. So this is a well-known kind of represent. If you see, it is a data structure, the memory allocation for that. So it is similar to the a stack. Last in will be whichever is calculated innermost will be taken out first or something like that. So it is a last in, first out. Okay. Now let us try to see how it is being implemented here. Okay. So if you see the recursion, analyze of recursion. So there are, we'll see, what is the time complexity of that. Okay. In case of a time complexity, iteration, if it is n, the say factorial, I want to calculate a factorial of n, which n itself is very big. Okay. So you're calling a loop within a loop, loop within a loop kind of. Okay. So it takes a time complexity is going to be, is it a linear? Can you tell me if it is a polynomial, if I want to do a factorial, okay, of a n, is the time complexity will be linear or how it will be varying? Can you tell me?
Yes, ma'am, it will be linear.
Will it be linear? Just check. If I've got a phi, okay, I have to calculate that phi or factorial of phi into that whatever I'm doing, but I have to calculate 1 minus minus minus. So within that loop I had to go there. So carefully you put that. So there will be a increase in that, but no doubt there is an increase. But in what way it is going to be increase? That is important there. Okay, we'll see that. In case of a recursion, so it is a assuming everything is a constant, we try to figure out the number of time a recursive call is being made. Okay. So a call made to a function, say what is this? It is not O. Do you remember this? O of 1. O of 1 means it's a fetching, your time complexity representation. So hence the n number of time the recursive call is made makes the recursive function O of 1. Though you are calling only once, but you are calling in iterative manner, so it is going to be the O of n. Okay. Now coming to the space complexity. Now coming to the space concept, how much memory, okay, you're going to use that. Okay. The amount of extra space required for a module to execute. In case of iteration, because you're calling one within another, the compiler hardly requires any extra space. Okay. The compiler keeps updating the value of variable. This is something like I said as a stack. Okay. Used in the iteration. But in case of a recursion, the system needs to store activation record. Okay, each time it calls. So it is similar to stack. You have to maintain that. Okay, the order has to be maintained. So that extra complexity is required to maintain that. So there is a time complexity as well as a space complexity in that. Okay. So what happens to the factorial of this? Say for example, if I take a factorial of a function. So if I want to take a factorial of 1, there is no much complexity. But if I want to increase the factorial, n is increased, okay? So it is a closed form for us, okay? So it is a, I can calculate just the multiplication for this. Now what happens if there is n equal to, I can implement the same thing with a recursion kind of, okay? So directly I can implement for loop, I can go, okay? I can just use the for loop and calculate that, or I can use this kind of representation and I can calculate. This is more suitable for a recursion part, okay? Now this is how I can represent by the recursion, okay? So you're just checking it is not equal to 0. This is the condition. It's a base criteria to come out of the function. This is a must for us, okay? Otherwise you're returning whatever you entered into the factorial. Again you are calling the same function with decrementing that. So you're calling a function within a itself until n is going to become a 0. But don't forget to decrement here. If you don't decrement, you will, it is a continuous function because you're not coming out of this loop at all. So it is not a similar to the I can execute the same thing with the for loop also, okay? We call that kind of implementation as a iterative. This is a recursive in nature. So recursive is calling a function itself, okay? I'm calling a function within itself. The same function is being called, okay? So we call the name as a recursive. I can implement the same thing with the for loop also. So this is how we call this as a iterative. I'm initializing and I'm incrementing one by one, and I'm going with the until whatever the condition is met. I'm calling, but I'm not calling the same function. This is what it differs, okay? Everything I'm controlling by this iterative manner. This is a loop condition, but this is not calling itself. But if you see the recursive, this function has to be called again within itself. So with the condition, some value are passing, but that value has to be checked always, or there should be criteria to come out of this factorial. That is an important point there. I hope it is clear for you. So there is any concept I can represent by recursive manner, not always. Wherever we have a chance of calling itself or a repetitive in nature, we can go with a recursive implementation. But same thing can be implementable by the iterative implementation also. That is a loop kind of. So if you see that, if you compare both of them, so iterative algorithm uses a looping, which we discussed with the for branching, because we have to use this if condition. This is a must. This is a base criteria which we are told. And this is a progressive approach. What do you mean by progressive? Each time I should reach to this, okay? I should be one step closer to this, okay? So then only I can reach to this. Otherwise, I cannot reach to this condition. Okay. Sorry. So this is the important. In case of a looping, I have iterative manner, but in a recursive algorithm, we'll be having a if condition branching structure. So recursive solution often less efficient in terms of time and space. Why? Because it's whatever the complexity increases, but recursion can simplify the solution of a problem, often resulting in a shorter path. It will be because I need not use many variables there, okay? I'm using a same variable again and again, reinitializing, giving a different value to that, okay? So if you see that way, it is shorter, it is a faster way also, okay? But until if it is not implemented proper, it can lead to the looping. It is like if condition is not handled properly, then it can go to the very difficult condition, or it can go to the unlimited or any kind of that condition. So you have to be careful in branching structure. So this is a well-known example. So if I want to calculate a factorial of any number or something, I can call itself. The factorial is a function which we define, and I'm just calling the function here. But what is implemented in a factorial is more important. Let us take that. So factorial of n, any n you want to just check, but you have to check for the particular condition. This is a branching which I am referring to. Okay, so if it is greater than 1, then again call itself. Okay, you're calling but decrementing the value. This is important. Okay, you're calling itself. So n is multiplied with n minus 1. Next iteration, the whole information is temporarily stored and it is being multiplied by n minus 2, if you remember. Okay, because whole thing becomes a n here. Okay, until what? This condition is met. The moment n is equal to 1, you are returning 1 to that. Okay, so you are calling itself. So temporarily, if you see the memory utilization, same memory is being updated with the values here. Okay, that is what is done. You are returning to this, again coming to the same value here. Okay, so that is what is the memory utilization, but the condition has to be taken properly. So this is how you can see the memory utilization. So if I want to calculate the factorial of 5, then this is how we implement in the for loop. So first time this will be calculated, 4 is being calculated, sent again, and you are calculating 3 here, and again 3 is multiplied with the 2 factorial or something until it returns the 1. This is how I'm telling about the stack here. So stack, if you see the stack here, so you're just calculating the initial, the last value is 1, then it is multiplied with the its values, previous values. That is how the stack, if you remember the stack representation, this is how it is going to work. Is it clear? If you see the recursive memory utilization, is it fine? Did you follow? Yes.
Yes, ma'am.
Okay. So
Yes,
yeah, stack, you have to remember the stack representation. So first, until you receive the 1 here, then the whatever is being multiplied, then it is calculated together. Okay, that is how it is done. Okay. Now this is again the well-known information or Fibonacci series, what we call. So what you are trying to do, if I can calculate the subsequent numbers, so I can get the subsequent, it is basically the Fibonacci series. Whenever I do, I'm just calculating the previous 2 values and again getting a next values. Okay, so it is again, but the implementation is not like your factorial. Okay, we'll see that how it is done. So initially it starts with 0, then 0 and 1, 2 information will be there, and you're adding these 2, that is what you're getting here, and next one it is being added with the next 2, and these 2 will be added, 3 will be generated, 2 3 is added, and it is 5 is generated, so on. Okay, so that is how the Fibonacci series is being done. So you are taking the last 2 information and trying to do some arithmetic, the plus operation, and getting a new value to that. Okay. Okay, so this is the procedure. I don't go to the program as such. So this algorithm can be implemented in any of the programming concept. So what you're trying to do, you're trying to declare these 2. These are the base of seed we call. Okay, these are important for us. So you're setting this to 0, another to the 1 here. So what you're trying to do, whatever the n value they want, how many n value Fibonacci series you want, you can just loop for this. This is looping structure. Okay, but same thing I can do it with the your recursion part also. Then these seed values are being added and you got the things. Okay, now you are moving the seed values, initially whatever you declared as a 0 and 1 is being moved to the another new set of seed values. Okay, so that is how you can do it with the your recursive manner also. So in a recursive values, you are sending those to seed values and adding them, getting a new value of that. Okay, so only you have to think of what are the two previous values which has to be sent there. So this is how you can implement the same thing with the same thing with the your what do you say your recursion manner. Okay, so you're calculating the Fibonacci of n minus 2. That is what you're calculating for the n. So you're adding them and returning back. Okay, so until you get a reverse condition. This is in a reverse manner. Okay, so that is how you have done with the recursive implementation. You can implement by the for loop also. You can implement by the your what do you say recursive manner also. So I don't go with the detail of this. This is just the implementation of a same algorithm. Is it clear? Fine. You understand the algorithm. That will be helpful for you. You can implement that with the any of the programming language. So first you initialize your seed with whatever the values, and then add the previous two values and get one more value kind of. Okay, so it's a recursive in nature. So we can go until the your n values. But when you do it in a recursive manner, you require to do it in a reverse way. Okay, so you can do the recursive implementation for that. What is important to understand is this concept. Okay, so you have to know what you mean by iterative algorithm, how it works, and a recursive algorithm, how it works. Okay, is it clear for you? Fine. Yes.
Yes, ma'am.
Okay. So that is for today's class. So any doubt you can ask. So today, just to recollect, today we started with our concept on a linked list. Okay, how to implement a polynomial addition and a multiplication using a linked list. So we have shown the power of your dynamically representing the memory, or how we can utilize the linked list for effectively implement the addition or a multiplication of a linked list. Okay, so that is the concept. Another one we have discussed about a recursion and how it is different from a iterative manner. So for loop or a while loop, how it is different, and what all the care has to be taken for a to represent a recursive algorithm. Is it clear? So if you just to see the summarize the data structures as such, so we have covered a array, we covered the stack, queue representation, circular queue, okay, and then we touch upon the linked list. Again, we have seen the different implementation of that, say for example, single link and double linked list and all that. And then we see the how the recursive algorithm can be used, basically the stack which we use there. Okay, stack representation. So we try to represent the, or we are able to operate the information or memory in a stacked concept. So that is a recursion problem what we have done. So how it is different from a iterative algorithm, say for example looping construct. Okay, so that is what we till now we covered with our data structure. Is it clear for you? Any doubt in this pertaining to this part? Yes, students? Is it fine? Any doubt? Yes or no?
Yes, ma'am. It's clear.
Okay. So that is about our data structure for today's class. So I'll just take. So next class we will be having a quiz also Tuesday, and we'll start with some other concept, new concept. Okay, fine. Thank you. Thank you for the. Otherwise, I'll conclude the
Thank you,
class.
ma'am.
Okay. Take care.
Thank you, ma'am.
Thank you.
Ma'am, could you please upload the slides today itself possible because we have the quiz on Tuesday.
Yeah, I will put it and not in a slide mode. It will be in a PDF mode. Is it fine?
Yes, ma'am. Thank you very much.
Okay, I'll do that.